curious minds, welcome back to ProjexCellence ProDigy, your one-stop solution for all your project management and mechanical engineering concepts. I am Govind, a certified PMP and mechanical engineering professional. So far, we have understood the Otto cycle, where heat is added at constant volume, and the diesel cycle, where heat is added at constant pressure. But here is the big question. Do real engines follow either of these perfectly? The answer is no. Real engines actually follow a combination of both, and that is called the dual cycle. In today's lesson, we will understand the working of the dual cycle and derive its thermal efficiency step by step. So let's get started. Dual cycle is an air standard thermodynamic model that combines constant volume heat addition like the Otto cycle and constant pressure heat addition like the diesel cycle. And that is why it is called the dual cycle. Let's understand its processes. First, we have process 621, the intake process. Here, the piston moves from TDC to BDC. The intake valve is open and the exhaust valve is closed. As the piston moves downward, fresh air is drawn into the cylinder. Since this air comes from the atmosphere, the pressure inside the cylinder remains almost constant at atmospheric pressure. That is why this is called a constant pressure intake process. Next comes process 1 to 2, isentropic compression. The piston now moves upward from BDC to TDC and both valves are closed. The air is compressed to a very high pressure and temperature. Since this is an ideal process, there is no heat loss and all the work done on the air is converted into internal energy. As a result, pressure rises sharply and temperature increases significantly. And this high temperature prepares the system for the next stage, combustion. Now let's move to the most important part of the dual cycle, heat addition in two stages. First, we have process 2 to X. Here, constant volume heat addition. At this stage, the piston is very close to TDC and both valves are closed. Fuel is injected into the hot compressed air and it ignites almost instantly. Since the piston has not yet started moving, the volume remains constant. Because of this, the pressure rises very sharply and the temperature increases significantly. This process is similar to the Otto cycle because heat is added at constant volume. And heat added in this process is Cv Tx minus T2, here Tx minus T2. We also define a pressure ratio which we denote with alpha, and alpha is Px divided by P2. This represents how much the pressure increases during this rapid combustion phase. Next comes process X to 3, constant pressure heat addition, here. Now the piston starts moving downward from TDC. Combustion continues, but this time it happens gradually. As heat is added, the gases expand, so the volume increases while the pressure remains approximately constant. This process is similar to the diesel cycle because heat is added at constant pressure. And the heat added in this process is Cp T3 minus Tx, here T3 minus Tx. And we define the cutoff ratio which we denote with beta, and beta is equal to V3 divided by Vx, here V3 divided by Vx. This indicates how much the volume increases during this stage of combustion. Next, we have process 3 to 4, isentropic expansion. here 3 to 4. At this stage, combustion is complete and the gases inside the cylinder are at very high pressure and temperature. Both the intake valve and exhaust valve remain closed and the piston now moves downward from TDC to BDC. As the hot gases expand, they push the piston downward and produce useful work. And this is called the power stroke of the engine. During this process, the volume increases while the pressure and temperature decrease. Here no heat is added or removed in the ideal cycle. So this process is called isentropic expansion. Next comes process 4 to 5, constant volume heat rejection. At the end of the power stroke, the piston reaches BDC. At this point, the exhaust valve opens and the high pressure gases begin to escape rapidly. This causes a sudden drop in pressure, which is called exhaust blowdown. In the ideal cycle, this process is represented at constant volume heat rejection because the piston is momentarily stationary at BDC, so the volume remains constant. During this process, pressure drops sharply and temperature also decreases. After that, we have process 5 to 6, constant pressure exhaust. Now, the piston starts moving upward from BDC to TDC. The exhaust valve remains open while the intake valve stays closed. As the piston moves upward, it pushes the remaining exhaust gases out of the cylinder. Since the cylinder is connected to the atmosphere, the pressure during this process remains approximately atmospheric. During this process, piston does work to expel the gases and this is not the useful work. So we called it negative work or pumping work. Its purpose is simple, to clear the cylinder and prepare it for the next cycle. Now let's understand the temperature entropy diagram of the dual cycle. On this diagram, the vertical axis represents temperature and the horizontal axis represents entropy. Process 1 to 2, isentropic compression. You can see a vertical line going upward, which means entropy remains constant while temperature increases. Next, we move from 2 to x. Here, heat is added at constant volume. So here, entropy increases and temperature rises sharply. This part behaves like the Otto cycle because heat is added at constant volume. Then from x to 3, heat is added at constant pressure. Here, entropy increases further and temperature continues to rise. This part behaves like the diesel cycle because heat is added at constant pressure. Now, from 3 to 4, we have isentropic expansion. This is a vertical line downward, means entropy remains constant while temperature decreases. This represents the power stroke. And finally, from 4 to 5, heat is rejected. And here on the TS diagram, the curve moves downward and to the left. Entropy decreases and temperature also decreases. So what we know, the vertical lines on this diagram represent isentropic processes. And the rightward movement represents heat addition. And the leftward movement represents heat rejection. And the area under these curves represent the heat transfer in the cycle or work done. Now let's derive the thermal efficiency of the dual cycle step by step. We start with the basic definition of efficiency. Efficiency equals heat supplied minus heat rejection divided by heat supplied. QS minus QR divided by QS. In the dual cycle, heat is added in two stages. First, for process 2 to x, heat is added at constant volume, which is mCb. 'Tx' - T2. Here, Tx minus T2. T2 - T2. 'T' 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 - T Second, for process X to 3, heat is added at constant pressure, which is mCp T3 minus Tx. Here T3 minus Tx. So total heat supplied becomes mCv into Tx minus T2 plus mCp into T3 minus Tx. Next, heat is rejected during process 4 to 5, which is at constant volume. So the heat rejection will be mCv into T4 minus T1. Here T4 minus T1. If we substitute Qs and Qr value into efficiency formula and simplify it further, so it becomes 1 minus Cv into T4 minus T1 whole divided by Cv into Tx minus T2 plus Cp into T3 minus Tx. Now, if we divide numerator and denominator by Cv, and since Cv by Cv is equal to gamma, so we get the efficiency formula is 1 minus T4 minus T1 whole divided by Tx minus T2 plus gamma into T3 minus Tx. Here, we don't directly use the temperature based efficiency formula. Why? The answer is simple. To use this formula, we need all the temperatures T1, T2, Tx, T3 and T4. But in real engines, these temperatures are not directly known and they keep changing with operating conditions. So instead, we express the efficiency in terms of ratios: compression ratio, pressure ratio and cutoff ratio. These are designed parameters which are easy to measure and control. So we will derive this temperature formula further to ratios. We know compression ratio R is equal to V1 divided by V2. Total volume divided by clearance volume. Pressure ratio during constant volume heating. Here alpha is equal to Px divided by P2. And cutoff ratio during constant pressure heating. Here beta V3 divided by Vx. Process 1 to 2 is isentropic compression. Here we will apply the relationship Tb raised to power gamma minus 1 is equal to constant. So T2 by T1 is equal to V1 divided by V2 whole raised to power gamma minus 1. And we know V1 divided by V2 is R, compression ratio. So T2 by T1 we can replace here with R raised to power gamma minus 1. And from here T2 is equal to T1 R raised to power gamma minus 1. Process 2 to X is constant volume heating here. And as per ideal gas law, if volume is constant, then P by T is constant. So for process 2 to X, we can write Px by Tx is equal to P2 by T2. And we can rewrite it Px by P2 is equal to Tx by T2. And here we know Px by P2 is alpha. So Tx will become alpha T2 and T2 is T1 R raised to power gamma minus 1. So Tx will be alpha T1 R raised to power gamma minus 1. Process X to 3 is constant pressure heating here. As per ideal gas law, V by T is constant. So for process X to 3, we can write Vx by Tx is equal to V3 by T3. Or we can rewrite it V3 by Vx is equal to T3 by Tx. And we know V3 by Vx is beta, the cutoff ratio. So from here, we can write T3 is equal to beta Tx and Tx value is here. So it will be T3 is equal to alpha beta T1 R raised to power gamma minus 1. Process 3 to 4 is isentropic expansion here. So again we will use the relationship Tv raised to power gamma minus 1 is equal to constant. So for process 3 to 4, T3 divided by T4 is equal to V4 divided by V3 whole raised to power gamma minus 1. If we see this PV diagram, V4 is equal to V1. So we can replace V4 with V1. and beta is equal to V3 by Vx, or V3 we can write beta Vx. So here V3 we can replace with beta Vx. And another term here, V1 by Vx will be R, compression ratio. So T3 by T4 will be R divided by beta whole raised to power gamma minus 1. And from here, T4 value we can write T3 into beta divided by R whole raised to power gamma minus 1. If we simplify it further, T3 value we derived in previous slide as alpha beta T1 R raised to power gamma minus 1. So T4 will become alpha beta T1 R raised to power gamma minus 1 into beta divided by R raised to power gamma minus 1. And finally, T4 will be alpha beta raised to power gamma T1. Now we will substitute all temperature values into efficiency equation we had. So these are the temperature values we just derived in previous slides. So numerator becomes T4 minus T1 is equal to T1 alpha beta raised to power gamma minus 1, and denominator Tx minus T2 alpha T1 R raised to power gamma minus 1 minus T1 R raised to power gamma minus 1. So here T1 R raised to power gamma minus 1 into alpha minus 1. Similarly, T3 minus Tx alpha beta T1 R raised to power gamma minus 1 minus alpha T1 R raised to power gamma minus 1. And finally, it will be alpha T1 R raised to power gamma minus 1 into beta minus 1. So total denominator becomes T1 R raised to power gamma minus 1 into alpha minus 1 plus gamma, this one, into alpha T1 R raised to power gamma minus 1 into beta minus 1. And finally, we can write it T1 R raised to power gamma minus 1, alpha minus 1 plus gamma into alpha into beta minus 1. If we substitute numerator and denominator here, so our final formula of efficiency of dual cycle become 1 minus alpha beta raised to power gamma minus 1 whole divided by R raised to power gamma minus 1 big bracket alpha minus 1 plus gamma into alpha into beta minus 1. This formula shows how efficiency depends on four key parameters: compression ratio R, pressure ratio alpha, cutoff ratio beta, and specific heat ratio gamma. If you look at the final expression, the numerator represents heat loss and the denominator represents heat input. First, the compression ratio R. It appears in the denominator. As R increases, efficiency increases. This is because higher compression raises temperature before combustion, which will lead to better energy conversion. Next, the pressure ratio alpha. This represents constant volume heat addition. As alpha increases, the pressure rise is stronger and efficiency improves. Next, the cutoff ratio beta. This represents how long combustion continues. As beta increases, combustion lasts longer and efficiency decreases. Finally, gamma, the specific heat ratio. Higher gamma means the gas can convert heat into work more effectively. So, efficiency increases with gamma. And that is how each parameter affects the dual cycle efficiency. So now we have completed the dual cycle. It clearly shows how an engine converts heat into useful work in a more realistic way. Compression prepares the air at high temperature. Heat is added into two stages. First at constant volume like the Otto cycle, and then at constant pressure like the diesel cycle. Expansion of gases produces useful work, and the exhaust removes the burnt gases to complete the cycle. Finally, we saw the performance of the dual cycle depends on compression ratio R, pressure ratio alpha, cutoff ratio beta, and the specific heat ratio gamma. If you found this lesson helpful, don't forget to like, share and subscribe to ProjexCellence ProDigy. Namaste, goodbye, Sampai Jumpa.